Consider a vertical uniform circular motion. Okay, this is the center of a circle. This is a string. Okay, this is a string that performing vertical uniform circular motion in an anti-clockwise manner. Let's say this position here is A, this position is B, position C, D, and E. Okay, we are interested to know what happens to the tension values for this ball here that is swing from A to B to C to D to E and back to A. So in this case, how are we going to perform the analysis? Okay, I would like to teach you 4 universal techniques to solve almost all the uniform circular motion. That is very, very important. First step is draw the free body diagram. Okay, draw the free body diagram. Second is identify, you cannot forget all these, identify center of rotation or the acceleration, because center of rotation means center of acceleration, because we know that in circular motion all the objects accelerate towards the center of the circle. Okay, third is to resolve all forces along acceleration, that means along the center of rotation. Fourth, apply the Newton's third law, Newton's second law, F net equals to ma, and the a is v square over r omega square, or mv omega. Okay, these are the very important 4 steps in almost all the circular motions problem. Okay, now let's look at position A. What are the 4 steps? First, draw the free body diagram at position A. Let's say this is position A here. Now the ball is, okay, I take out the ball here. This one I draw here. So the free body diagram is tension and the weight, right? Okay, so what is the second step? Identify center of rotation. Where is the center of rotation? Everybody know this is the center, right? From this position, the center must be pointing upwards, right? That means they're accelerating upwards. So we just write beside here, acceleration is upwards. Next, resolve all the forces along acceleration. Is this T and mg along acceleration? The answer is yes. So we do not need to resolve. We just directly jump to the step 4. Just write down F net equal to mv squared over r. In this case, what is the F net? Is it T minus mg or mg minus T? Since the object is accelerate upwards, in other words, object accelerate upwards, that means the tension must be greater than the weight, right? So we say the F net equals to mv squared over r. The F net in this case is the T minus the mg equals to mv squared over r, and T equals to mg plus v squared over r. Okay, this is the first equation, let's say, for this system at position A. Let's do position B. How to draw position B? Okay, let me use different color to draw position B. Now at position B, now at this position, what is the free body diagram of this object here? Okay, let's draw B here. Let's draw B here. The B definitely is tension is to the center. The mg is down, right? The mg is down. You see, from here, we know the tension must in this direction. The mg is down. Okay, so in this case, where is the what about the second step? Identify center of rotation. So center of rotation is here. So what is the direction of acceleration? Definitely pointing towards the center of rotation. So in this case, I just draw pointing to the left. Third case, resolve all the forces along acceleration. Do you need to resolve the tension towards the direction of acceleration? No need, because it's already along the tension, along the acceleration direction, right? What about the weight? The weight is 90 degree perpendicular. You want to resolve mg towards the center? You can. You just mg cosine 90, right? But mg cosine 90, the answer is 0. So in other words, any perpendicular force acting to the acceleration, any perpendicular force here, they will not affect the acceleration. So we don't care about mg. So in this case, what is the force that caused acceleration? Definitely only the tension, right? So tension equals to mv squared over the r. Okay, let's say this is the second case. Okay, second equation. Now let's do the third one. The third one, let's say the position C. Okay, draw the free body diagram as C. So definitely there must be mg downwards, right? But do you still remember here? There's the string here. The string can only pull, cannot push. Some students draw up. Actually, the tension is down. So in this case, it must be mg down. The tension also down because string can only pull the object. Okay, so in this case, first step is done. What about second step? Identify center. So this is the center. So the acceleration is pointing downwards. So it's pointing downwards. What about the third step? Do we need to resolve the forces? No, because they are already along the acceleration. So we say F net equal to ma. The F net is just T plus mg equals to mv square over r, right? So this is the third equation. What about object D? Okay, let's look at object D. Object D is much complicated because this one you need to draw free body diagram of this object at this position is mg is downwards, then the tension is pointing towards the center. Okay, so we just draw here, the weight is down, the tension just point there. Okay, so in this case, where is the center of the rotation, center of acceleration? Center is here, so we know that the acceleration must be pointing this direction. Right now we need to resolve all the forces along acceleration, but now in this case, tension, yes, is already along acceleration, but mg is not, right? So mg is not. We need to resolve this towards this center of acceleration. So let's say this angle is theta. Okay, I forget to give you this angle theta. Let's say this angle alpha. So in this case, this theta, this alternate angle is theta. This also must be theta, right? So how to resolve mg towards the center? Must be mg cosine theta, right? So this is theta. So let's resolve mg towards this direction of acceleration. So in this case, the resultant force is T plus mg cosine theta, because after you resolve it to a center, this is mg cosine theta component. It's mv square over r. This is equation 4. What about the last equation? What about the last equation for E? Okay, let's draw for E. Let's do together E. This is the mg. This is the tension. So we know that this is alpha. So what you should do? Okay, let's draw the E here. Now very simple. So this is the E. So this is the tension. This is the weight. This is the alpha. We know that. Okay, first step is done. Second step, identify center. So we know that this is the center. So it must point towards the center, right? So point to the center. This is acceleration direction. Okay, this is the acceleration direction. So third step, resolve the forces. Tension is already along acceleration direction. However, mg is not, right, the weight. So we need to resolve weight towards this direction because this weight can resolve to this and this, right? So weight must resolve towards here. So this one become w cosine alpha, right? W cosine alpha. So how to draw the free the F net equal to ma? So in this case must be T minus the mg cosine alpha equals to mv square over r. Okay, this is the fifth equation, let's say. Now, I have a few questions for you. First, tell me, which position has the highest tension? Take your time to look at it. Obviously, the answer is A. A, because you see this equation 1, T is mg plus v square over r. The rest are smaller in magnitude. This one never plus, right? This one minus somehow. This one is actually T equal to mv square over r minus mg, right? This one is the same. T equal to mv square over r minus mg cosine theta. This one is T equal to mv square over r plus mg cosine alpha. But cosine alpha is less than 1. So relatively, this is smaller than this object at point A. So A has the highest tension. If you are not sure, please take a calculator and go and count, okay? Which point has the lowest tension then? See carefully. Which point has the lowest tension? The answer is C. Okay, C. Look at this one. This is minus. That means the tension here is the lowest. What is the meaning of tension lowest? Tension lowest means that there's a very high chance that the object, when going up, they will just fall down. They will just fall down without doing circular motion because the tension almost zero. Almost zero means it's just fall down. They won't be have a tension here when it's as the highest position. Okay. Now, so please remember, the lowest tension is at the highest. The highest tension is at the lowest of the circular motion. For this uniform vertical circular motion. Now, let me ask you the third question. Tell me, which point has the highest centripetal force? Can you think about it? The answer is every point has the same centripetal force. Okay, why so? What is centripetal force? Do you know that this is centripetal force? Do you know that this is centripetal force? Oh, these are centripetal force. You see? Everywhere is equivalent to mv square over r, right? In other words, every point here has the same centripetal force. It's just that at this position here, who provides the centripetal force? T minus mg provides the centripetal force. Who provides the centripetal force at position B? Who provides the centripetal force at position B? That means there's only T provide the centripetal force at position B. At C, who provides the centripetal force? It's the T plus mg that provides the centripetal force. E is this one. I hope you understand what I'm saying. In other words, this is the force, this is the cause, okay? The left side is the cause. In other words, this is the cause of the circular motion. mv squared over r is just a centripetal force, which is a force that makes things turn. But in this case, at this position C here, at this position C, who makes the object turn is both the tension and the weight. However, at position B, who is the one, which force caused the acceleration, the centripetal acceleration? The answer is only the tension. Only the tension provides centripetal acceleration, not the weight. The other position all have tension and weight, okay? In this case, all have tension and weight except this position. So I hope you understand. Tension can vary, as a conclusion, tension can vary in the uniform vertical circular motion. However, they have the same centripetal acceleration, same centripetal force, okay?